This is Andromeda, but not the faint smudge you might have seen in the night sky. What you are looking at is the closest giant galaxy to our own, a sprawling island of stars drifting through the DAC, 2.5 million light-years away. And one day, it may collide with the Milky Way. It's easy to forget that this glowing cloud hides a universe of its own. Every tiny point of light, every grain of cosmic dust, is an entire star. Each star likely has its own planets, its own moons, its own frozen comets and burning asteroids. Each one is a system with its own history, its own storms, its own ancient chemistry. And together, they form a city of hundreds of billions of suns, suspended in silence, drifting steadily toward us through the void. Andromeda matters to us because it is more than a neighbor. It is a mirror, a way to understand what our own galaxy may have looked like from the outside. Its spiral arms, its star-forming rings, its ancient core, all help scientists decipher how galaxies grow, transform, and endure the violence of cosmic time. And its future is tied to ours. In billions of years, the Milky Way and Andromeda will begin a slow dance of gravitational attraction, spiraling closer until the two galaxies merge into one. But before that distant future arrives, there is a deeper story. A story of how humans first discovered this mysterious glow in the sky. A story of telescopes, forgotten astronomers, revolutionary insights, and the greatest images ever created of another galaxy. A story of ancient collisions, tidal streams, and the chaotic forces that shaped Andromeda into what it is today. In this video, we will explore all of it. How Andromeda was discovered, what modern telescopes reveal about its structure, what scars remain from its violent past, and what its future collision with our own galaxy might look like. This is the journey into the heart of our nearest cosmic giant, an odyssey from Earth's first glimpse of a nebulous smear to the breathtaking clarity of modern astronomy. Welcome to Andromeda. For most of human history, Andromeda was nothing more than a pale blur in the night, a delicate, ghost-like smudge in the constellation of the Chained Princess. Ancient astronomers saw it as a nebulous cloud, a faint patch on the sky that refused to sharpen into a star, no matter how hard one stared. To them, it was simply an oddity, something softer than a star, brighter than empty darkness, but belonging to neither. For centuries, that was all we knew. Then came the age of telescopes. In the early 17th century, when the first lenses were turned toward the heavens, Andromeda finally came into focus, but only just. Through these primitive instruments, it remained a hazy oval, still called a nebula, still thought to be a nearby cloud of gas within our own Milky Way. Yet even this dim improvement ignited curiosity. Astronomers sketched its shape, described its glow, debated its nature, but no one yet imagined that this soft blur hid an entire galaxy. The 19th century changed everything. With larger telescopes, and eventually with the birth of astrophotography, Andromeda began revealing its true form. In 1888, Isaac Roberts captured the first long-exposure image of the mysterious nebula, and the result stunned the scientific world, a clear spiral structure twisting outward like a cosmic hurricane. Suddenly, Andromeda wasn't just a cloud. It was a complex, organized system. But even then, the question remained. Was this spiral a part of our own Milky Way, or something unimaginably larger? The answer arrived in the 1920s, carried by a special kind of star, the Cepheid variable. These stars pulse in brightness at predictable intervals, allowing astronomers to calculate their distance with extraordinary accuracy. When Edwin Hubble identified Cepheids inside the Andromeda Nebula, he measured their true distance, and the result shattered the known universe. They were over 1 million light-years away, far, far beyond the edge of the Milky Way. With that single discovery, the illusion collapsed. Andromeda was not a nebula. It was a galaxy, a colossal island of stars like our own, floating independently in the cosmic ocean. Overnight, the universe expanded. What we once believed was the entire cosmos suddenly became just one galaxy among countless others. Andromeda rewrote our understanding of reality. One faint, ancient blur on the sky had quietly held the key to a much bigger universe, and once revealed, it changed everything. Now that we've explored how humanity first uncovered the truth about Andromeda, we can finally answer the question, what exactly is this colossal object hanging beyond our sky? Andromeda is not close by any human standard. Its soft glow reaches us from more than 2.5 million light-years away, light that began its journey long before the first humans walked the Earth. And yet, in the scale of the universe, Andromeda is practically next door. It is the nearest giant spiral galaxy to us, a neighbor existing just far enough to remain unreachable, yet close enough to study with extraordinary detail. If we could somehow drift alongside it, the first thing we would notice is its size. Andromeda spans roughly 150,000 light-years from end to end, making it slightly larger and more massive than the Milky Way. Its disk is wide and elegant, curling into sweeping spiral arms that stretch around a brilliant central region. Each of these arms is packed with stars, hundreds of billions of them, along with glowing nebulae, dark dust lanes, and vast nurseries where new stars ignite. At the heart of this galaxy lies its nucleus, a region so dense with stars that they blend together into a golden blur. Hidden deep within this radiance sits a supermassive black hole, quietly anchoring the galaxy with its immense gravity. It does not need dramatic flares or violent outbursts to reveal its presence. The stars themselves orbit in patterns that betray the invisible mass at their center. Scientists often call Andromeda the Milky Way's older, heavier sister. The comparison fits. Both galaxies are spirals. Both possess bright bulges, sweeping arms, and halos of ancient stars. But Andromeda is slightly more massive, slightly brighter, slightly more evolved, a mature version of what our own galaxy may one day resemble. And ironically, we understand Andromeda in some ways better than we understand the Milky Way. That's because we view it from the outside. We see its structure clearly, its arms, its rings, its dust, its core, while our own home galaxy hides its shape behind clouds of gas and interstellar dust. Studying Andromeda is like stepping outside your own house for the first time and finally understanding its shape. It is our laboratory for learning how spiral galaxies form, age, collide, and rebuild themselves. Andromeda is not just a neighbor. It is a window into our own past and a quiet preview of our distant future, an entire island of stars drifting through the darkness, slowly, inevitably moving toward us. For decades, Andromeda was a beautiful mystery, vast, complex, and frustratingly out of reach. Even the most powerful ground-based telescopes could only reveal broad strokes: the shimmering disk, the dark lanes of dust, the glowing core. Earth's atmosphere blurred the finer details, making the galaxy look soft and distant, as if seen through a layer of moving water. Beautiful, yes, but limited. Everything changed when we lifted our eyes above the atmosphere. Space telescopes like Hubble, Galax, Spitzer, and Chandra opened new windows into Andromeda, each one revealing a different part of its anatomy. In ultraviolet light, we saw clusters of hot newborn stars blazing blue against the void. In visible light, Hubble traced the sculpted spiral structure with astonishing clarity. Infrared observations exposed the cold dust woven through the disk, forming dark river-like streaks that feed star formation. And in X-rays, Chandra revealed the high-energy heartbeats of the galaxy, stellar remnants, neutron stars, and the quiet power of the central black hole. But even with these breakthroughs, astronomers faced a challenge. Andromeda is too large to fit into a single photograph. Its vast disk stretches wider than the field of view of any space telescope. If Hubble tried to capture the whole galaxy in one shot, it would see only a fraction, like trying to photograph a cathedral through the keyhole of a door. The solution was as elegant as it was ambitious: a giant photo mosaic. Over the course of nearly 10 years, Hubble took hundreds of overlapping images of Andromeda, each one a tiny tile in an enormous cosmic mural. Piece by piece, the galaxy came together, over 600 individual frames stitched into a single panorama containing billions of pixels. The final result was unprecedented, the most detailed view ever captured of another galaxy. For the first time in history, we could zoom in and see individual stars in a galaxy outside our own. Not just bright supergiants or clusters, ordinary stars, resolved one by one, like grains of sand scattered across a cosmic beach. The resolution was so unbelievably high that scientists described the project as a census of Andromeda, a way to study its stars the way one might study the population of a city, neighborhood by neighborhood, street by street. This clarity didn't just give astronomers a better picture. It transformed Andromeda from a distant spiral into a living system we can analyze star by star. Each point of light carries clues about age, composition, motion, and history. Together, These clues form a story far richer and more detailed than anything we could have imagined even a decade ago. Andromeda went from a mysterious blur to one of the best understood galaxies in the entire universe, all because of a mosaic built from hundreds of tiny pieces. When we look closely at Andromeda, not as a distant swirl of light, but as a living, evolving system, the first thing that stands out is its vast stellar disk. This is the great rotating structure that defines the galaxy's shape, a flattened plane of stars, dust, and gas that stretches out in immense spiral arms. These arms are not static decorations, but dynamic regions where gravity, turbulence, and chemistry weave new stars out of collapsing clouds. Here the galaxy continuously renews itself. Within these spiral arms lie the birthplaces of stars, luminous blue clusters glowing with the fresh heat of creation. These young stars burn hot and bright, standing out like sparks scattered across the galactic disk. Their color reveals their youth. Blue stars live fast and die violently, and their presence tells us that Andromeda is still very much alive, still forming new stellar generations. But the most striking features of Andromeda's star-forming regions are its rings, vast, circular structures carved into the disk like ripples frozen in time. The outer ring, located far from the galactic center, is one of the most active regions of star formation in the entire galaxy. It shines with an abundance of young, massive stars whose intense ultraviolet light floods the surrounding gas. This ring is not simply a pattern, it is a record. It tells us that something once disturbed the galaxy, sending a shockwave outward that ignited the birth of new stars. Closer to the center lies another structure, the inner ring. For years, astronomers mistook it for a tightly wound spiral. Only with modern imaging did we realize it is a genuine ring, formed by the same ancient forces that shaped the outer one. This inner ring is packed with warm dust, young stars, and intricate streams of gas flowing under the influence of Andromeda's gravitational tides. It is a dense, crowded environment where stellar nurseries form in thick clusters. What makes these rings particularly important is the chemical signature of the stars within them. Many of these young stars are metal-rich, meaning they contain abundant elements heavier than helium. This is a vital clue. Metals are produced only in the cores of earlier generations of stars, and spread through the galaxy when those stars die, especially in the explosive violence of supernovae. So when we see metal-rich newborn stars, it means Andromeda has lived through multiple cycles of star birth and destruction. It is an old galaxy, enriched by countless supernova remnants, its interstellar medium seeded with the ashes of previous stellar eras. And this leads us to one of the most evocative ideas in Andromeda's story. These rings are not ornaments. They are scars. They are the frozen waves left behind by ancient impacts, shock fronts created when smaller galaxies plunged through Andromeda's disk long ago. Like ripples radiating from a stone thrown into a pond, these rings map the places where the galaxy was shaken, disturbed, and reshaped. The rings of Andromeda are not symbols of harmony. They are evidence of survival. Through them, we can trace the galaxy's turbulent past, and the echoes of those ancient collisions still shine today in the light of newly born stars. When we look at Andromeda's elegant spiral shape, it is tempting to imagine a galaxy that has lived a peaceful life. But Andromeda is anything but peaceful. It is a cosmic survivor, a galaxy shaped, scarred, and rebuilt by a long history of violent encounters. In astronomy, collisions are not rare accidents. They are the engines of galactic evolution. Large galaxies routinely swallow smaller ones, tearing them apart with gravity and weaving their stars into new patterns. And Andromeda has done this many times. The evidence is written across its halo and disk like ancient wounds. Far beyond the bright spiral arms, faint rivers of stars stretch outward into space, stellar streams that arc and twist like ribbons of light. These streams are the remains of smaller galaxies that wandered too close and were shredded by Andromeda's gravity. Their stars now move along elongated, graceful paths, still following the ghost of the orbit their original galaxies once traced. Each stream is a story of destruction, a reminder that even entire galaxies can be broken and scattered. Some of these streams form enormous, looping structures, so long and diffuse that they can barely be seen without sensitive surveys. Others appear as tight, well-defined arcs. Together, they form a kind of fossil record in Andromeda's outskirts, a record of every companion galaxy it has ever consumed. Closer to the disk, the signs of impact become even clearer. The massive outer ring of star formation, the smaller inner ring, and the asymmetric dust lanes all hint at ancient collisions. These rings behave like the ripples created when a stone splashes into a pond, circular waves of gas and stars driven outward by the shock of impact. Their symmetry and scale reveal that the intruding galaxy must have plunged almost directly through the center of Andromeda, shaking the system to its core. Many astronomers believe that some of Andromeda's surviving satellites, small, faint dwarf galaxies orbiting nearby, are only remnants of once larger systems. Their outer layers may already have been stripped away. Their cores may represent the last, dense pieces that resisted Andromeda's gravitational pull. Others may have been consumed entirely, their stars now blended into the rings or scattered through the halo. These ancient collisions did more than rearrange stars. They reshaped Andromeda's very identity. Every time Andromeda absorbed another galaxy, the impact stirred up vast clouds of gas, compressing them and igniting bursts of star formation. Entire generations of stars may have been born in the aftershocks of these encounters. Some of the young, metal-rich stars we see today, especially in the Great Rings, owe their existence to the violence of these long-forgotten events. So the Andromeda we see now, majestic, luminous, and beautifully structured, is not the result of steady, gentle growth. It is the product of chaos, a galaxy forged through turbulence, rebuilt repeatedly by forces large enough to reshape entire stellar populations. Its rings, streams, and distorted structures are not flaws. They are the scars of its past, the echoes of every galaxy it has ever devoured. And in a universe where nothing remains untouched forever, Andromeda stands as a reminder that even the most graceful shapes can hide long histories of collisions, upheavals, and rebirth. Surrounding the vast, luminous disk of Andromeda is a hidden kingdom, a swarm of smaller galaxies that orbit their giant host like a scattered flock. These satellite galaxies, most of them faint dwarf systems, drift through Andromeda's gravity while the way small birds circle around a great soaring predator. They are part of Andromeda's extended family, but also its future meals. Astronomers have identified dozens of these dwarf galaxies, each one containing only a tiny fraction of the stars found in Andromeda. Some are compact and resilient, managing to retain their shape despite the immense gravitational forces around them. Others are already showing the strain. Their stars are stretched into elongated trails, their outer layers stripped away, their original structures warped and bent. These distortions are not random, they are signs of surrender. Every dwarf galaxy orbiting Andromeda is slowly losing mass, piece by piece. As they pass close to the mighty spiral, its gravity pulls at them relentlessly, peeling away their stars and adding them to Andromeda's halo, its rings, and its streams. What remains of these dwarfs eventually becomes only a dim core, a fragile remnant of what once may have been a substantial system. Some satellites are already in the process of dissolving. Their stars drift into extended arcs that stretch across the sky, forming new stellar streams that wrap around the galaxy like pale, ghostly ribbons. Others still hold their shape but are destined for the same fate, caught in the gravitational embrace of a neighbor far too massive to resist forever. In many ways, the relationship resembles life in the wild. Around a great beast, there are always smaller creatures moving in cautious orbits, feeding in its shadow, surviving for as long as they can. Some stay at a safe distance, some wander too close, some, over time, are simply absorbed. Andromeda's satellites are no different. They represent the final stages of a long cosmic hierarchy, tiny galaxies circling a titan, each slowly giving up their stars, their identity, their history, until one day they merge into the greater whole. The Andromeda we see today is not just one galaxy. It is a collection of many, an entire ecosystem shaped by the slow dance of gravity, where smaller members of the flock gradually lose themselves in the wings of the giant at the center. As enormous as Andromeda is, its greatest significance may lie not in its past, but in its future, a future that is entwined with our own. For millions of years, astronomers have known that Andromeda is not sitting still in the sky. It is moving. Slowly, steadily, almost imperceptibly, the entire galaxy is drifting toward us at more than 100 kilometers per second. In the scale of human life, that motion is meaningless. But across billions of years, it becomes destiny. Andromeda and the Milky Way, the two giants of the local group, are on a long, inevitable trajectory that may one day end in a cosmic embrace. Not tomorrow, not in 1,000 lifetimes, but in the distant future, billions of years from now, the two galaxies may meet. When galaxies collide, the event is nothing like the violent crashes we imagine. Galaxies are mostly empty space. Stars are separated by vast distances, so vast that even during a head-on collision, almost no stars will physically hit each other. Instead, the drama unfolds through gravity. The two galaxies will pass through each other repeatedly, like ghosts, stretching their spiral arms into long tidal tails, throwing stars into new orbits, and stirring their gas into turbulent waves. Each pass will distort them further. Their graceful spiral shapes will twist and warp. Their disks will thicken and stretch. Immense clouds of hydrogen will slam together, triggering new bursts of star formation. Blue, newborn stars will ignite like sparks across the sky, fueled by the compression of gas stirred up by the encounter. Eventually, after several passes, gravity will slow their motion and pull them together permanently. The result won't be a spiral galaxy at all. Simulations suggest the merger will create something larger, rounder, and more diffuse, an immense elliptical-like system, brighter and heavier than anything either galaxy could have become alone. Astronomers sometimes call this future galaxy Milky Way, a symbolic fusion of both names. But what about us? For the solar system, the collision is unlikely to be catastrophic. Our sun will not crash into another star. The universe is simply too large and too empty for that. But our orbit around the Milky Way's center will change dramatically. We may be flung into a new path, drifting farther from the galactic core, or swept closer toward regions that are now unfamiliar. The night sky would glow with strange new constellations, new clusters, and the blazing arc of Andromeda's stars mixing with our own. It is a transformation on a scale far beyond anything our species will witness. This is a story measured not in years or centuries, but in billions of years. And yet, even now, we have the tools to see it coming. By measuring the motion of Andromeda's stars, by studying its rings, its streams, and its orientation in space, astronomers can simulate the future of our cosmic neighborhood with remarkable precision. The collision of the Milky Way and Andromeda is not just a distant possibility, it is a predictable chapter in the long history of galaxies. And thanks to our observations today, we already know how that chapter might unfold. As our journey through Andromeda's story draws to a close, one question remains. Why does this galaxy matter so much to science? Why do astronomers devote decades to studying a world so distant that its light began traveling when early humans were barely taking shape? The answer is simple and profound. Andromeda is our mirror. The Milky Way is difficult to study from within. We live deep inside its disk, surrounded by gas, dust, and billions of nearby stars that obscure the galaxy's true structure. But Andromeda offers what our own home never can, a clear, external portrait of a large spiral galaxy very much like ours. By studying it, we learn what the Milky Way looks like from the outside, and how galaxies of this size form, change, and endure. To astronomers, Andromeda is a laboratory on a cosmic scale. It lets us observe the entire life cycle of stars, the glittering nurseries where they form, the aging populations in the disk and halo, and the remnants of stars long gone. Its rings reveal the physics of shockwaves and collisions. Its stellar streams show how galaxies devour their neighbors. Its companion dwarfs help us understand gravitational tides and satellite evolution. Its central bulge and core teach us about the growth of galactic nuclei and the behavior of supermassive black holes. Andromeda is, in many ways, a complete case study of galactic evolution, from the quiet birth of stars, to the violent reshaping caused by ancient mergers, to the slow gravitational dance that will eventually bring it toward us. But perhaps the most powerful idea is this. The history of Andromeda is the history of every major galaxy, including our own. Its scars hint at the collisions the Milky Way has already survived. Its bright young clusters reveal the processes still active in our galaxy today. Its long-term trajectory foreshadows an encounter that will one day reshape our cosmic neighborhood. When we look at Andromeda, we are not just seeing a distant island of stars. We are looking at a possible future of the Milky Way, a preview of what our galaxy might become after its own mergers, collisions, and rebirths. And so the final note of this story is both scientific and poetic. When we raise our eyes to Andromeda, we are not looking at a stranger. We are looking at one of the possible future faces of our own home.